Hi, today we are going to talk about physics-informed neural networks or PINs. I'm Gautam Kapila, a machine learning enthusiast. What we'll do today is first look at a few concepts in feed-forward neural networks, followed by the idea of PINs or physics-informed neural networks, what they are and how do they work, and then essentially we're going to conclude. So, um, in the key concepts for feed-forward neural networks, what we look at the basic idea, the multi-layered perceptron, the backprop, and the loss function and the learning algorithm. And finally, we'll review all of them together as to how they work. This will form foundation for understanding the whole idea and the principle behind physics-informed neural networks. So let's go. The basic idea of neural network approach is to approximate a function f star between input vector x to output category y. That is, y star, y of hat is f of star x. Now, as you can see on the image on the right side, if one has multiple inputs x1, x2, xn, they are multiplied by corresponding weights to a neuron, and this multiplication is effected through matrix operation in which you have multiplication with weights and addition of a bias term which goes to an input of a neuron, and the output is generated through an activation function which could be a sigmoid or many others that exist. So, so basically, we have a mapping between inputs and output y hat, which tries to approximate the relationship between input and output. And, um, and this mapping is driven by the choice of W's and B, which we call theta, the parameter theta, essentially, which consists of weights W and bias B. Theta is learned by iterating over the data. And in a multi-layer perceptron, input data is processed over multiple layers of neurons. Each layer I of neuron is associated with implementing a certain function, f of I, and finally the data actually follows from input to output in feed-forward nature in one direction only, and is essentially generated through chaining of multiple functions, f of 1, f of 2, and f of 3. So y would be given by function f of 3 or function f of 2 or function f of 1 of x. So, and the whole idea is that given a sufficient depth of layers and number of neurons, we can approximate y or with a functional form that represents x1 to xn. So let's now look at what the backpropagation is. Now, backpropagation refers to the method of computing the gradient. It is essential to training the neural network to learn from the data. Now, gradients are, if you look at a scalar function, fy is equal to f of x is given by f dash of x, which is dy by dx. And as can be seen from the figure on the right, it essentially points to being a slope at a given point in the plot. And gradient of a vector function y as a function of x, but where both y and x are vectors, is given by Jacobian matrix such that j of ij, the individual element of those matrices, is given by dou xj of f of xi. And in context of pins, to basically understand why we're going through all of this, is that the idea of availability of gradients y1 and y2 is very essential. This is the first key ingredient that allows us to impose physics on neural networks and do physics-informed neural networks. So moving on, the other important aspect on this is loss function and learning algorithm. Now, loss function is measure of deviation or inaccuracy or cost you want to minimize. The choice of loss function depends on nature of problem. For example, MSE for regression or cross entropy for binary or multi-class classification problems. And it is defined by mathematical expression L theta, where theta are the parameters representing the weights and the biases as we looked at before. The learning algorithm here refers to gradient descent technique used to adjust the weights to minimize L of theta. Since L of theta is a measure of deviation, we want to ensure that the cost or L of theta is minimized. And the direction of training of weights is in the direction of decreasing L of theta, and is given by theta dash, which is a new parameter set of a neural network, is related to theta minus eta gradient of L of theta, where eta is a learning rate. So here we actually come across two new essential ingredients for PIN. The first one is, or the second ingredient right now, is a loss function generation or construction of a custom L of theta. The third ingredient necessary for PINs, which we leverage, is the neural network's learning algorithm itself. So we looked at three key ingredients that help help in construction of a PIN, of physics-informed neural network. First one is availability of differentials. Second is loss function. Third is neural network's learning algorithm. And how that is done is something we're going to look at. But let's just quickly recap. So we have an input X that generates output Y of hat. We compute a loss function associated with respect to actual target variable, and just adjust theta so that the Y of hat is as close as can be to Y. Now, in this framework, basically it boils down to now trying to figure out how can we impose constraints of physics and above. Now, and that's essentially leads us to the physics-informed neural networks. And what we're going to do in this section is understand the role of physics first in database learning, and then using physics in neural network. What's the big idea? And then we look at an example, how it is being done. The role of physics and data. Now, there are three scenarios that are in front of us when we try to solve a data-driven problem. One in which there's lots of data and no physics. This is not the problem that is being attacked by PINs, or physics-informed neural networks. This is typically a big data problem where other techniques are useful. Now, the other extreme is shown on the right, which is little data and lots of physics. This is typically the domain of classical experimental physics, where we collect some data, we fit a model, and we try to explain the world around us. We don't have a lot of data, but we have very good understanding of the correlation and the functional dependencies between different parameters. So, but then there's in-between space where we know some physics. We generally believe this is what the governing equation should be. And we have some data, not lots of data and not very little data, but the data could be noisy. The data, and maybe we don't have all the boundary conditions, and so on and so forth. So this is the space where physics-informed neural network can play a huge role. And this space is growing. So let's look at what it actually boils down to. So using physics in neural network. So let's try to understand what we mean by physics here and how we can use it. So physics, simply put, is essentially study of matter, energy, and its properties, like we probably all relate to. And what really happens is, in this, the mathematical framework on which physics rests is essentially the differential equations, which describes the interrelationships of different material properties. So if we look at a heat equation as an example on the right hand side, in one dimension, it provides a relationship between temperature as a function of time and distance. Here capital T is the temperature, small t is the time, K by rho C is basically diffusivity, and X is distance. And so it is this mathematical framework of differential equation which is used to describe the physics around us, which is actually used to impose the physics on the neural networks. And we'll look at it very quickly. But before we do that, let's just spend a little more time on the idea of differential equation and what this is. Here we have a second order differential equation given by a d square y by dx square plus b dy by dx plus cy equal to 0. And we have two boundary conditions that allows us to solve this differential equation uniquely. And this is given by y of 0 is y naught and y of 1 is y. Um, Typically, traditionally we have had two ways of solving this. One is through analytic solution. For simple equations like above, we have direct analytical solutions. However, we could have differential equations that is nonlinear and more complicated and cannot be solved, something which cannot be solved analytically, where we try to break up a big complicated differential equation into smaller linear equations which can be solved and use finite difference method to solve it. Now, in addition to these two, what is evident more recently is there's a third approach, which is the neural network based approach. And this was introduced, and there have been two basically key papers that have led to a lot of research in this. And first is the 1998 paper by Lagares et al. In IEEE Transactions Neural Networks. And in 2019, Risey et al. In Journal of Computational Physics. And it is this approach that we're going to look at right now. Okay, so now to solve these problems in which constraints are driven by physics, let's look at suitability of neural networks. So first key element needed to support this is we should have a way to support any functional form of the solution y hat is f of star of x. Now this is actually supported through neural networks through the idea of universal approximation. Second, we should have availability of derivatives so that we can construct a differential equation and arrive at a solution easily. Now, derivatives are readily available in the neural network through the backprop and the Jacobian and chain rules. Third is a question we have to ask ourselves: can neural network work as an optimizer, wherein we could train neural network to actually provide y hat as a solution? And the answer is yes. And what we're going to look at now is how. So let's look at neural network as an optimizer. So here we have X input going through the feed-forward neural network structure and generating y hat. And let's assume y hat is equal to neural network of X and is a full functional form of solution to the differential equation. If y hat is a full functional form of the solution, the question is, how can we train the weights to arrive at y hat? So this is actually very cleverly solved by creating a custom loss function. Now, in typical loss function, we have L of theta, which is essentially a difference between y and y hat. And that loss is minimized to generate new weights and train the neural network. To solve the differential equation and so that y hat satisfies the governing equation, what we have now is we create loss function to include residual of the differential equation, the initial condition fit, and the boundary condition fit. And these three additional constraints, when added in loss function, help solve the differential equation. So for example, in the equation we have looked so far, a d square y by dx square plus b dy by dx plus cy equal to 0. minimizing the residual of the differential equation essentially means minimizing this function. Since this whole differential equation on the left hand side is supposed to be equal to 0, the difference or the value of this itself needs to be minimized and should be as close as 0, which is what the first term is. The second terms are essentially consists of the boundary condition fit, in which y hat 0 minus y naught square plus y hat 0 minus y1 square is minimized. And this is minimizing the error in the initial, and minimizing the error in the initial condition is not needed, as we don't have an initial condition for this. This is a boundary value problem itself. So now let's look at how a partial differential equation is solved using a neural network. So this is again from Risey's work, and we have Berger's equation, which is a fundamental partial differential equation occurring in various fields. For example, fluid mechanics, gas dynamics, etc. In 1D form, where u is a function of t and x, it is given by u of t plus u of x minus 0.01 by pi times uxx equal to 0, where x can range between -1 and 1 and t between 0 and 1. And the initial condition we have to solve to is u of 0x is minus sine pi x, and boundary condition we have to solve is for any t between 0 and 1 at x equal to -1 and x equal to 1, the value of u of x of t is 0. So, and how can we now use our ideas to solve this equation? So in this case, we have two inputs, x and t. It's a partial differential equation. So a neural network essentially consists of x, t, and theta, and we have multiple layers, and it provides u hat of t of x as an output, which is considered a solution to the problem. Now, through backprop, we do have available derivatives of u of t of x with respect to dou t and dou x, dou square by dou x square, and we also have the identity matrix, which essentially allows us to construct our own loss function tied to the differential equation residual itself and the boundary condition, initial value condition, and the boundary condition. And this loss is minimized to receive to get the optimal parameters that actually solve the equation. And it turns out that this is very easy to implement in TensorFlow. First, we define the neural network u of t of x, and then we define the pin, which essentially can be done as shown here. The gradients are directly available in the TensorFlow, so we can construct the equations and compute the loss. Now here's a solution to the equation. The equation is solved by computing RMSE over initial and boundary condition, minimizing it. So in this plot, you have on the x-axis t and on the y-axis x, and u of t of x is this whole 2D space. These cross points are essentially the data on which the neural network is trained, and this consists of boundary condition and initial condition. Initial condition is when t is equal to 0. And the solution that we get is shown for 3 different times and between x equal to -1 and 1 at t, which is essentially t equal to 0.25, 0.5, 0.75, and we see that the prediction, the red dots, actually perfectly are matching the exact solution which we know. So clearly this approach has worked and is an elegant way to use a neural network as an optimizer with constraints driven through physics equation to solve this. So this is the whole idea of physics-informed neural network. And to conclude, PIN uses knowledge of governing equation in deep learning. And it opens the possibility of developing data-efficient and physics-informed learning systems, finding wider applications in scientific computing. NVIDIA and ANSYS are already using it, and the area is likely to grow. You can find more information on this topic if you're interested in the references. And essentially, the group that published 2019 paper from Brown University has a lot of information on it. With this, I'd like to close the talk. Thank you for your attention.